All right. So 7.4 is known as integration by partial fractions. So we're doing this one. We're basically, when you're thinking about partial fractions, it's basically taking, if we look at the problem like 1/4 plus 1/2, we have to get a common denominator to put them together. So 1/4 plus 1/2 would be 2/8 plus 4/8, and you put them together, and or you can do it to fourths or eighths, doesn't matter. You put them together, you get 6/8 or 3/4. So you'd have to put them together. Partial fractions is actually taking that fraction and splitting it apart into two separate pieces so that all the numerators are going to be constants instead of variables. So it allows us to be able to split apart a fraction, and then we're looking at the integration of each of those pieces. So here's a good example with actual letters and numbers. So if we take the 2 over x minus 1 and 1 over x plus 2, if I wanted to get multiply those or put them together, I need a common denominator. So I just multiply the denominators. So the x minus 1 times x plus 2. And then what I have to do is I have to multiply the tops by the same thing. So that 2 is multiplied by x plus 2, and that 1 is multiplied by x minus 1. So my fraction, when I put it all together, will be x plus 5 over x squared plus x minus 2. That's what you used to do when you're trying to get one fraction. What we need to do is we need to go from this piece here back to that first part. That's the hard part of partial fractions, is how do we actually get back there easily. So that's what we're going to look at today. So the reason why we want to get back there is because if I do it back to this piece here, these fractions right here are really easy to integrate, because it's basically just you make the bottom a u, it's all going to cancel out when we do the du anyway. And when you have 1 over u, it's the ln. So when you get a simple fraction with a constant on top and a linear polynomial on the bottom, you actually get a simple integration, where this first integration would be quite complicated to do out without being able to do it this way. So let's look at how to actually do the simple one first. All right. Step one, when we're doing this, is we have to do long division, because what we want to do is we want to get the top down to something less than what the denominator is. So if you don't remember how to do long division, because it's been a while since most people have done long division, we're going to do it out together. So long division, you take the bottom. So I have x minus 1. And we have the x to the third plus 0x squared plus x plus 0. Whenever I'm doing long division, I always put the zeros in for the pieces that are missing, because we're probably going to need those spaces anyway. And if you don't have it, you're going to have to put it in later, and it makes your life a little more confusing. So I always fill in the blanks with the zeros. So now we're looking at what do I got to multiply by x to get x to the third, which is x squared. So I multiply x to the third minus x squared. Then we change our signs and put them together. So the first part should always cancel out. So I'm left with now x squared plus x plus 0. I do it again. X goes into x squared once, so that's x. So I have x squared minus x plus 0. Change my signs. And I get 2x plus 0. X goes into 2x twice, so it's plus 2. So I get 2x minus 2. Change my signs. And I'm left with 2. So this integral is now x squared plus x plus 2 plus 2 over x minus 1. Doing it out by long division. Questions with that? Everybody vaguely remember how to do long division? All right. Now that we've done the long division, we can go through and break up and do the integral of each piece. So the integral of x squared, x to the third over 3, integral of x squared over 2, integral of 2 to x. And now I've got this one is a constant over a linear term. So it's just plus 2 ln of x minus 1 plus c. You always want to do long division to start, as long as the numerator is bigger than the denominator, the degrees. So as long as the degree of the numerator is bigger than the denominator, you have to do long division first to pull out all that rest of the stuff. Once the numerator is a lower degree than the denominator, then we actually go through and do out our calculations. Even if it's the same, you have to do it. So it's got to be less than when you're doing it out. So in this problem, we actually did not have to do partial fractions because the final term that I had in the last fraction was already a linear term. Questions with that one? They only get harder from here, so.
I don't have a question with this one specifically, but the last term, that 2 over x minus 1.
Yep.
There was an example in the book where it's 2 over x minus 1 squared. And they got something that I just have no idea how they got for the integral of that.
Well, so it's the x minus 1 parentheses and squared on the outside?
Yeah.
All right. Well, we're going to get to that, and I'll show you how they do that one.
Okay.
We're going to do one similar to that one. So, because there's rules when you're working with it, when there's multiple terms of the same things, you have to break it up in a different way. Because if you add like 1/2 plus 1, or let's say 1/3 plus 1/3, you get 2/3. So to try to break that back up, it's not always necessarily going to be the same term on top because you end up losing the bottom piece. So we have to do something a little bit different to the top of that one. But we'll do one similar to that.
Okay.
All right. So as you can see here, this is the example I just did. So these notes are all in line, so you can easily pull these down. So, all right. So the other thing that we have to do is when we have the denominators, you want to factor them completely out. So for example, if you had q to the 4th minus 16, we want to factor that one out. Going down to x squared minus 4 and x squared plus 4 isn't far enough. You want to break it down as far as you possibly can factor it out. So this one would break down to x minus 2, x plus 2, and x squared plus 4. So you want to get it down into multiple factors because that's how we're going to be splitting up our fractions. Because those denominators are going to be all those pieces there. So that's why, if you remember at the beginning when I was talking about setting up for this chapter, I says make sure you know how to remember how to do long division, factoring, and then some systems of equations we're going to actually work with as well. The next thing we're going to do is we're going to break up our problem into partial fractions. So as you can see here, this one's just a over my linear term. And then I have ax plus b. When this is a quadratic or higher, we actually have to add the x's to the tops. Because you always want it to be one less the degree on the top than it is underneath it. And we'll see how that works in a couple examples. All right. First case. There's actually 4 different cases we're going to work on. The first case that we're going to look at is when I can break the denominator up into all distinct linear factors, which means all to the first power or degree of 1. And no factor is a multiple. So like the example you just asked where you had x minus 1 and it was squared, that would be a constant multiple of another. So there's going to be multiple versions of those. So in this first example, we're going to look at them where they're all separate, distinct linear factors. All right, so when we break it up, that means there's a constant for at the top of each one. So remember, it's got to be one less than the degree on the bottom. So if the degree on the bottom is a linear term, one less would be a constant for the top. So the key is being able to find those constant terms at the top. All right. So let's look at this one. So the first thing I'm going to do for this problem is we want to look and see if I can actually do long division first. And in this case, the numerator is one less than the denominator, so I cannot do long division. So the next thing we're going to look at is we want to factor out the denominator. So let's break up this denominator. So I have 2x to the third plus 3x squared minus 2x. So I can pull out an x. I have 2x plus 3x, or 2x squared plus 3x minus 2. And then I factor that one out, and I get 2x minus 1 and x plus 2. So now I've completely factored the bottom out. So my new integral that I'm going to have is going to be something over x. We'll call that a. Something over 2x minus 1. And something over x plus 2. We've now got to figure out what the a, b, and the c are. To figure that out, basically what I'm going to do is I'm going to look at what each one of those letters is multiplied by, and then figure out the coefficients that match up with the other problem, with the numerator up top. So I have, if I was to bring this back together, basically, I have a times 2x minus 1 and times x plus 2. I have b times x and x plus 2. And I have c times x and 2x minus 1. So we got to multiply these out, these linear terms. So I get 2x squared plus 3x minus 2 is x squared plus 2x, and 2x squared minus x. So I've got a. So if I want to get the x squareds basically together. So for x squared, I've got 2a plus b plus 2c. So everybody see where I got those? So that's from that, and that. That's the x squareds. Now I want my x term. Now my x term. So x is going to be 3a plus 2b minus c. And my constant term is going to be minus 2a. Any questions where that all came from? Okay, I'm either getting really good at explaining this, or I've totally lost everybody, and you don't want to ask why. All right, so if we look at my original problem, the term in front of x squared the constant in front of x squared, the leading coefficient, is a 1. So that means 2a plus b plus 2c has to equal 1. The coefficient in front of x is 2. So that means 3a plus 2b minus c has to equal 2. And the constant term at the end is -1. That means -2a equals -1. So I can figure out a really quickly right now. I know this, so a has to be 1/2. Because if I divide both sides by -2, I get a. Since I now know a, I can plug that into the other two problems, so I just have the b and the c to work with. So in this first equation, that's going to become a 1, so I know that b plus 2c equals 0. And that's going to become 3/2, so I know that 2b minus c equals 1/2. We still good? Okay, so we've got b plus 2c equals 0, 2b minus c equals 1/2. So a simple way to do this would be elimination. So I can multiply the first equation by 2. So that whole first one by 2. So I get 2b plus 4c equals 0. And then I could subtract the two problems. So I end up getting 5c equals 1/2. So c is 1/10. Now that I know that c is 1/10, I can plug it back into the one with 0 and figure out b. So I have b plus 1/5 equals 0. So b equals -1/5. And I have my three values for a, b, and c. We're getting there, I swear. All right, so my new integral so my integral now that I'm going to work with is the integral of 1/2 over x plus 1/5 over 2x minus 1, and then minus 1/10 over x plus 2. So that's my new integral. So to do the integration for these, remember, anything over is, it's just going to be the ln. So this becomes 1/2 ln of x. Since there's a 2 in front of there, I do have to, that one ends up, that one comes out. So it's going to be a 1/2 in front of it. So I get 1/10 ln of 2x minus 1. And then I have minus 1/10 of ln of x plus 2 plus c. And that's my answer. So if you are good at doing the system of equations, you can get your values there pretty quickly. If you're like most people and haven't done systems of equations in quite a while and are not very good at doing systems of equations, I'm going to give you a second way that you can find the answers to these problems, which is typically the way that I end up doing it. But the reason I show you that one first is that one logically makes the most sense when you're looking for the values, because we're basically taking it and those are the coefficients in front of each of the ones. So it kind of makes sense on why that's the way it does it. So if I showed you the second way to do it, it wouldn't necessarily, you wouldn't automatically make the connection between the two of them. So what I'm going to do is we're going to take the original problem that I had. So I have a, and then 2x minus 1, and x plus 2, plus b, x, and then x plus 2, and plus c, x, and 2x minus 1. And that equals, it has to equal the top. So it has to equal the x squared plus 2x minus 1. So those two have to equal each other. So another method that we can do is by picking values for x that are going to cancel everything out for me. So if I pick a value for x and it's going to cancel a bunch of stuff out, I can then solve for that, the letter that's left. So the first x that I'm going to do is we're going to say x equals 0. So I'm going to plug 0 into all of my x's. And as long as I do it to both sides of the equation, it's not going to change my problem and it'll still work. So this means I have a minus 1 times 2. The b, this cancels out because of that x. So b is gone. The c cancels out because of that x. So that equals, that's gone, and negative 1. So that means a is going to end up being the 1/2 like we had before. So I plugged in 0 to every single one of those x's all the way across, and that's all that was left. The next one I'm going to plug in, oh, not a, is x equals negative 2. So if I plug in negative 2 to all the x's, well, that's now going to become 0, so that's all gone. That now becomes 0, so that's all gone. But the c is not. So I have c times negative 2 times negative 5 equals 4 plus negative 4 minus 1. So this ends up coming out to be 10c equals negative 1. So c equals negative 1/10. And the last x I'm going to plug in is 1/2. When I plug in 1/2, the 2x minus 1s are all going to cancel each other out. So I get b times 1/2 times 5/2 equals 1/4 plus 1 minus 1. So I get b to the 5/4 equals 1/4. So that means b equals 1/5. And I get the same 3 answers for A, B, and C that I did before. So either method works. They both come up to be the exact same answers. Just depends on which method you like. I typically do this one. Most of the time it works out as long as you can easily cancel a bunch of stuff out this way. Sometimes you might get down to like 1 or 2 variables left that you have to find, and then you have to just do the system for those couple. But for the most part, you can use this way to get rid of quite a few of the actual values that you need. Questions with either of those? All right. That's case one. Still 3 more to go. All right, so we did example 2. All right, case 2 goes to the situation where I was asked before, where we have values where the ones down the bottom are going to be repeated. So where we have x minus 1 squared, for example. That's actually the example we're going to do with it. So if I have a linear pair or linear term which is repeated, I have to repeat that term, but I'm going to do it as pieces. So the first one's going to be just the linear term. The second one's going to be it's squared, and say it was to the third power, I'd have the same term again to the third power. So you actually have the denominators are going to be out each of those values, or the first one, second one, third one, all the way up to whatever the power happens to be. So if it was squared, I would just have 2. If it was to the third power, I'd have 3. If it was to the rth power, I'd have r of them. So that's how we deal with it, because we can't, if we left them all just as a single term, when I found my denominator at the end, I wouldn't have the denominator that I wanted, because I would just have what the single term was, where what I really wanted was the square root of that value. So that's why we have to repeat them. The top stays the same, though. It's still just A, B, C, and all down the line, depending on how many we have. So here's a quick example. We have x squared and x minus 1 to the third power. So I'd have x and x squared. And then x minus 1 to the third power, I'd have x minus 1, x minus 1 squared, and x minus 1 to the third power. So that's how we'd write it out. We're not going to do this one out because it's a lot of letters, but that's how we'd actually write out ones with multiple denominators like that. Does that kind of answer the question on what we're doing with it? I know we're going to go through and do one out, but that was probably what the confusing piece was.
No, I get that part. It's just once you do the system of equations, say D comes out to equal 2. It's just once they actually did the integral for that, they lost me. It came out to like -2 over x minus 1, and I don't know if you got that.
Gotcha. Okay, then I'll show you. That's not a problem. Yeah, because those are not going to end up being ln's because it's not to the first power. Gotcha.
Okay.
All right. Let's look at example 4. That's not what I wanted to do. All right, so let's look at this example and do it out. Okay, now, first step we always want to look at is, do we have to do long division? So this one, my numerator is to the fourth power, my denominator is to the third power. My numerator is not less than my denominator, so I have to do long division. So let's do out the long division. This was not the class that you need to have, that you should have a broken wrist for. Okay, so x to the third goes in x to the fourth once. So I have the x. I have x to the fourth minus x to the third minus x squared plus x. Change my signs. So I have x to the third minus x squared plus 3x plus 1. X to the third goes into x to the third once. So I have x to the third. Change my signs. So I end up, the first one cancels out, the second one cancels out, I end up with 4x, and the last one cancels out. So the integral I'm going to do is x plus 1 plus 4x over x to the third minus x squared minus x plus 1. So that's the integral that we're actually going to work with. All right, the next step we want to do is we want to factor the denominator. So x to the third minus x squared minus x plus 1. This one's one of those easy ones you can factor by grouping. So I have x squared out of the first one, which gives me x minus 1. I'm going to take out minus 1 out of the second one, and most with x minus 1. So I have x squared minus 1, x minus 1. The x squared minus 1 becomes x minus 1, x plus 1. So when I factor out or do that bottom piece out, my new integral is going to be x plus 1 plus 4x over x minus 1 squared, x plus 1. So now we're going to work with that. All right, are we good to there? Because I got to switch screens. Okay. Actually, let me do this first. Okay. All right, so I'm just going to work on this part right here. I'm going to ignore the first part for a little bit. So this part right down the bottom, I'm going to have x minus 1, a, plus b over x minus 1 squared, plus c over x plus 1. So now when I do out my pieces, I have a times x minus 1 times x plus 1. I have b times x plus 1. And I have c times x minus 1 squared. And that has to equal 4x. All right, so if I plug in, let's do it that way. We can plug in 1.
With the x minus 1 under the b, it's just x minus 1. It's not squared, right?
No, it is squared.
Oh, it is squared?
Yeah. Yeah, it's squared. Hold on, let me move my mouse pointer out of the way.
Where did it come from? Like, I see it under the 4x, x minus 1, and I see x plus 1.
Yeah, there was a square next to that x minus 1 squared.
Okay.
So, right, hold on.
But then when it got split up, it would just be...
So that's the x minus 1 squared.
Uh-huh, so it's 2 x minus 1s.
Right, so the case 2 states when I write it out, I have to write it out as x minus 1, x minus 1 squared. I have to go up each term.
Okay.
So here, I'll put back over to the slide real quick. I'll show you that slide. So if you notice, like right here, see how they got the x minus 1 to the third power?
Yeah.
I have x minus 1, x minus 1 squared, x minus 1 to the third power. You have to write them all out. Because remember, the whole goal is to get back to that original fraction. So the original fraction had an x minus 1 squared in it. So if I just left them as both a over x minus 1 and b over x minus 1, they already have a common denominator. I never have to make them squared. So that's why one of them has to be the x minus 1 squared. Otherwise, you won't get that piece.
Okay.
The other thing is when you're doing out the pieces down the bottom, notice how the a doesn't have an x minus 1 squared on it because it already had one of the x minus 1s in the bottom. So it's just multiplied by x minus 1 there. And the b doesn't have an x minus 1 at all because it has the x minus 1 squared. I didn't need that first term.
Okay.
So when we're trying to go backwards to the other problem. All right, so now let's pick some numbers to plug in. So this one, we're going to pick 1 and -1 as my first couple of values. I'm going to plug in, see what I get. So if I plug in 1, this side's 4. This piece is gone. And I'm left with 2b. So that means b equals 2. If I plug in -1, the a is gone because of that one. The b is gone, so this side's -4. But I'm left with the c. So c is going to be -2 squared, which is 4. So I end up with 4c. So c equals -1. Now, I've already, so the reason why we chose 1 and -1 is because I have those parentheses to cancel things out. I don't have anything else I can plug in to get rid of parentheses now. But I already know what b and c are. So I can plug those values in and basically cancel out those terms. So I'm looking for that x term right there. So if we're looking at that for that x, so 4 has to be, this one was going to be a x squared minus 1. And then b x plus 1. And c is x squared minus 2x plus 1. So if you notice, the a isn't on the x at all, right? There's no x term in for the a. It's not going to come out to be 0. Or did I miss one? Hold on a second. Where was it? So, all right. So I've got ax squared, and then I've got plus c x squared, and that has to equal 0. So the x squared equals a plus c. So I know a plus c is 0. I know c is -1. So a minus 1 equals 0. So a has to equal 1 to make it work. So once we've got the b and the c, I can just plug it into one of the values of the a's to find my a value. Does that part make sense?
Yep.
All right. Okay. Next piece. So my integral was x plus 1 plus. I'm writing it and then I'll switch over so you guys can see it. So no, I'm writing and you're not seeing what I'm writing. All right, so there is my new integral that I am factoring out, or that I'm integrating. Got factoring stuck in my head. All right, so let's go through into each of these pieces now. So the x is going to be x squared over 2. The 1 is just going to be x. Now, I'm going to actually do the next two completely out so you can see it, because I think that's the piece that was missing somebody or a few people out probably. So the x minus 1. So if I'm doing the integral of 1 over x minus 1 dx, I'm going to set u to be x minus 1. So that means du is just 1. So I'm really doing the integral of 1 over u du. which is ln of u, correct? So that becomes the ln of x minus 1, which is what we've been writing in the problem for the first couple ones that we did. So this one's just plus ln of x minus 1. That's why that one is just the ln of x minus 1. Now, let's take the same problem, the same steps here, but let's do that 2 over x minus 1 squared. If I did the same thing with the u, this integral becomes the integral, so I can put the 2 on the outside just to get rid of it, over u squared. Since it's not just a u and it's a u squared, I can subtract 1 from that too. So this becomes negative 2, 1 over u, because it becomes u to the negative 1th power. So that's why that one ends up being negative 2 over just x minus 1. And then the last one is again just 1 or just ln of x plus 1. Does that make sense now?
Kinda. I mean, what if it was to the third?
Then it would be the same concept. It would be just it'd be 1 over, it would end up being negative 2, so it would end up being negative 4 to the 1 over u squared. Because in essence, what you're doing when you're doing the integral of, let's just do this. Yeah, that's fine. When you're doing the integral of, say, u to the negative 3rd power, right? That's going to become negative 2 u to the negative 2nd power, which in this case u was x over 1, so that would be negative 2 over x minus 1 squared. Since it was just negative 2, when I added 1 to that, I got negative 1, which is why there's no exponent on that bottom piece. That makes sense?
Yeah. I'll sit with it for a minute too and just sink it in.
Okay, that's fine. Because everything else has the ln's in it, and that's why it's like that one piece gets a little confusing. It does. All right. Okay, so that's case 2. One other thing you can do, and I typically don't do it, is when you have ln's, you can combine them. So if it's subtraction, it's really division. So that's how they get the x minus 1 over x plus 1, because that was ln of x minus 1 minus ln of x plus 1. So they just put it together as division. So you can do that. The first answer was completely acceptable, though. All right, case 3. So the next case is where we have quadratics that we cannot reduce. So let's say I had x squared plus 4. Can't break that down any further. So I still need a way to work with that. So the numerator has to be exactly 1 degree more than the denominator. So if I have an x squared down the bottom, my numerator has to be ax plus b. So here's an example of that. So let's say I got the term, it's x over x minus 2, x squared plus 1, x squared plus 4. My first one is going to be just like we were doing before, a over x minus 2. Straightforward. But this one's got an x squared, so I've got bx plus c above it. This one's got an x squared, so I've got dx plus e. So I'm going to have multiple letters above those. Now, if you get a integral that has a constant over x squared plus a squared, since I'm going to have to do u substitution to get rid of that bottom, I need an x on top. If you do not have an x on top, then this is the formula for the integration. It's going to be 1 over a, the integral, the inverse of tangent, x over a plus, and then plus c, obviously. So that's going to be the one where if you don't have an x and you can't do the u substitution for it, which I'm going to show you in a minute, that's how you'd actually do that part to break down it. All right, so just make sure to have that written down. All right, next problem. All right, so we have 4x squared minus 3x plus 2 over 4x squared minus 4x plus 3. Now, so far, the two that we've done long division on, the denominator has been higher or lower than the numerator. This one, they're exactly the same. I still have to do long division. So let's do my long division first. So obviously it's only going in once. I change my signs. So I'm left with x minus 1. So the integral I'm going to work with is the integral of 1 plus x minus 1 over 4x squared minus 4x plus 3. Now I've got to factor the bottom. Of which I actually can't. So we actually can't factor it the straight way. So we're going to have to actually do a kind of a u substitution. We're going to change this into vertex form, and then we're going to do a u substitution or u piece from there. So, all right, so we got the, actually, because I'm going to save my hand. Go back and review how to convert a form from standard form to vertex form, and that's what you get. And what we're going to do is we're going to say u equals this. So I have u squared plus 2. And we're just going to say u is 2x minus 1. So that means du is 2 dx. So dx is 1/2 du. The other thing I need to figure out is what x is. So if I solve this over for x, I get x equals 1/2 u plus 1, because I'm going to need that for the top. All right, so questions about what I did there first before I plug it all into this integral, and you can see how this is all going to actually work out for me. So this is just changing it to vertex form. Look that up. And then basically I replaced that 2x minus 1 with a u. So this way I can actually do the process that we're going to be working out with it. All right. So I'm going to change my whole integration now. So we're going to actually pull this. The integral of 1 is just x, so I'm going to actually pull that out. So I have the integral. The x is 1/2 u plus 1 minus 1 over u squared plus 2 times 1/2 du. So I can change this. So that's, I'm going to pull out the 1/4. And I'm left with u minus 1 over u squared plus 2 du. So far, so good? All right, so now this one, when we're doing out this one, we don't have to do partial fractions in this one because it's already kind of basically done for me. So that's going to make this one a little bit easier, but this one I'm going to use to show you those other couple steps. So we're just going to do that integral part. All right. So now that I've got subtraction on the top in my denominator, I can actually split this into two problems. So I can do u over u squared plus 2. And I can do minus and then 1 over u squared plus 2. So I can split those two up now. So let's look at this first one. Let's do that first one first. So let's do this one. So I'm going to say, actually I can't use u now. So let's say m is u squared plus 2. So that means dm is 2u du. And I only have one u, so that's 1/2 dm is u du. So this integral right there becomes the 1/2 out front. The u is gone, and it's just 1 over u. So this becomes L or 1/2 ln of u squared plus 2. Oh, did I miss the? I forgot to write the 1/4 in front. So does that part make sense?
You don't even have to do all that, right? You can just know that the u
Yes.
squared is the 2u, and you have to add the 1/2 before.
Yes, you do not have to actually do that. You can do a lot of that implied. I just know I'm doing a bunch of the little steps, so I just didn't want to imply that everybody got that part. But yes. And actually, a lot of these ones, if it's just a simple one where you know it's going to cancel out, you just have to do your substitution, you know it's going to become the ln immediately. So it's like you can't actually just go directly from there right to that step. You can go directly to there without doing a lot of those intermediate steps. All right. The reason why I showed that out is actually more for this one over here. Because if I look at this one now, m was u squared plus 2, which is fine. dm was 2u. I don't have a u on top. So I can't do this substitution for that problem there. And that's why you needed that other, that tangent equation to break it out. So that piece over there, I needed, it was, it was 1 over a tangent -1 of x over a. So in this case, that integral right there is going to be 1 over the square root of 2, tangent negative 1. In this case, it's going to be u over the square root of 2 for that integration.
How do you determine what a is?
It's always the x squared plus a squared. This only works when you have the x squared plus a squared. So in this case, a was 2, so the square root of 2. All right, so now let's actually go through and write my final. So u originally in this whole problem was, where is it? 2x minus 1. All right, so now we can write our original problem out. So my integral for this problem is x plus 1/8 ln of 2x minus 1 squared plus 2 minus 1/4 square root of 2 tangent negative 1 of 2x minus 1 over the square root of 2 plus c is my final answer. All right, does that make sense? I know it's a ton of steps. There's a ton of things to remember, unfortunately. All right. We've got one more case to go. So we've looked at cases for all linear terms. We've looked at cases where linear terms repeat each other. That was case 2. Case 3 was where we had irreducible quadratics. And case 4 is where we have irreducible quadratics and that repeat. So it's actually the same concept as case 2, where you just have to do them multiple times. Except when we're doing quadratics, we have ax plus b on the top, so we have to repeat those as well. So we're going to actually do this example. Actually, I'm going to actually just work with theirs. Yeah, all right. So here's my integral. So the nice thing is this problem is already broken down for me. So I don't have to worry about breaking it down or factoring it out, which is nice. And I know the denominator is already bigger than the numerator because the bottom is going to be x to the 5th and the top is x to the 3rd. So we're good there. So now we can just go straight to breaking it up into partial fractions. So I have a over x plus, and then I have bx plus c over x squared plus 1. And then I have dx plus e over x squared plus 1 squared. Now, unlike the other problems where we'd be able to plug in values to get rid of my parentheses. This one, we're not going to be able to do that because you can't cancel them out. We could do it to the 1 with the x, but the rest of them aren't going to work out. So we're just going to multiply them out and do it out by systems. So I've got a times x squared plus 1 squared. I've got bx plus c times x squared plus 1. And then I've got dx plus e times x. So this one comes out to be a x to the 4th plus 2x squared plus 1. This one comes out to be b x to the 4th plus x squared plus c x to the 3rd plus x plus dx squared plus ex. So x to the 4th, the x to the 4th term, I have a plus b, and that has to equal 0 because there is no x to the 4th term. X to the 3rd, I have just c, and c, that's got to equal -1. X squared, I've got 2a plus b plus d, and that equals 2. The x term, I have c plus e, and that equals -1. And then the constant term, which is 1, I have a, and that equals 1. So this one actually works out pretty easy the way that they've got all the letters done, because I can use those letters to find the other ones. So like I already know that a is 1. So I know b has to be -1. I know c is -1. So that means e has to be 0, because that's the only value that would work there. And if I know a is 1 and b is -1, so that'd be 2 plus -1. Which is going to be 1. So that means d has to equal 1 in that case. So we can use the values that I got and not actually really have to go through and do the systems equations out. So my new integral that I'm going to be working with, now that I've got it all broken out, is 1 over x plus -1 or -x minus 1 over x squared plus 1 plus x over x squared plus 1 squared. And if I want to make it a little bit simpler, I'm going to take this negative sign out there and put it there, just so I don't have to worry about the negative sign in the problem. All right, so that's my new integral that I'm going to work with. So now we want to go through and split this up as much as possible so that I can actually work with it that way. So 1 second to split it up. Actually, let's do those. I'm writing it. So I have the 1 over x minus the integral of x over x squared plus 1 minus the integral of 1 over x squared plus 1 plus the integral of x over x squared plus 1 squared. So this one is just going to end up being ln of x. This one, when I do out the simple substitution, is also just going to be the ln of x squared plus 1. Oh, sorry, I forgot the half in front. One half ln x squared plus 1. This third one, because it doesn't have an x up on top, that's going to be my tangent one. So in this case, it actually, because a is 1, it ends up being just tangent, and the inverse tangent of x. And now this one, because it's squared, this one becomes 1 over 2 x squared plus 1. Because I remember I have 1 left, and that's where the 1/2 comes into play. Questions with that? Again, I know they're really long. All right, those are the 4 cases. And I'm going to end it there. So I'm going to stop this.